Hello everyone. Please enjoy watching this frog catch ants on the phone before we learn about selective reabsorption in the loop of Henle. So let's just think about where we are at. So we've gone through ultrafiltration in the Bowman's capsule, and then we did most of our selective reabsorption in the PCT. And now at the end of the PCT, remember we talked about how the concentration of our glomerular filtrate has not actually changed at all. The only thing that's changed is the volume. And now our filtrate enters the loop of Henle. The loop of Henle is responsible for the reabsorption of water and salts, so sodium ions, and that's what we're going to be focusing on in this next bit. So take a look at this diagram of the loop of Henle. The first thing that you need to understand is that the walls of the descending limb and the walls of the ascending limb are different. So if the walls of the descending limb, they're shown on this diagram as being thinner than the walls of the ascending limb, and that's just to represent the fact that the walls of the descending limb are thin and are highly permeable to water, whereas the walls of the ascending limb are thick and they are impermeable to water. So what does that mean? What it means is what is happening on one side affects what's happening on the other. So it's really important to be able to contextualize this whole process. So we know that this loop of Henle is completely surrounded by blood capillaries. Okay, we already know that. We've mentioned that like a million times. But not just that it's embedded in cells and it's all completely surrounded by tissue fluid. So if something leaves the loop of Henle, it then just dissolves in a fluid which flows around the whole nephron. It's really important you can visualize that, otherwise the whole thing won't really make any sense. So we need to start with the ascending limb. In the walls of the ascending limb, there are transport proteins that actively transport sodium and chloride ions out of the ascending limb and into the tissue fluid. This means that you have created a highly salty tissue fluid solution surrounding the loop of Henle. So the solution has a low water potential. As a result, water moves down its water potential gradient from the lumen of the loop of Henle out into the tissue fluid. This is passive osmosis. So if we just take a look at the solution, as we move down the descending limb, water is leaving. This is causing the solution to become more and more concentrated, and it's also causing the volume to drop. When we start moving up the ascending limb, we've got a highly concentrated solution, which is why we see at the very, very base, this is actually only for a very small area, we have a small amount of passive transport of sodium and chloride ions out. But then as you travel further up, we rely on active transport of sodium and chloride ions. So as we move up the ascending limb, the concentration of the solution in the loop of Henle drops. Can you see these numbers? So as we go down, it becomes more and more concentrated. And as we go back up, it becomes less and less concentrated again. So actually, the solution that enters the loop of Henle and the solution that leaves the loop of Henle is exactly the same concentration. The only thing that's changed is the volume. So let's just go through that process. So in the ascending limb, the sodium ions and the chloride ions are pumped out by active transport into the tissue fluid. Interstitial fluid and tissue fluid mean exactly the same thing. Remember, you've got active transport for like 90% of the time of the ascending limb and a little bit of passive transport right at the bottom, right near the apex of the loop of Henle. And the ascending limb is impermeable to water, so water cannot follow by osmosis, so no water can leave the ascending limb. But the movement of the sodium and chloride ions generates this salty solution, and therefore the water leaves the descending limb. And that's exactly what we're seeing here. So the descending limb is permeable to water. Now, you've also got a very small amount of movement of sodium and chloride ions by passive transport here as well, for exactly the same reason as on the other side, because it's becoming a highly concentrated solution towards the base. Now this water, as it leaves, it enters capillaries and it's taken away. And these sodium chloride ions, when they leave, they enter capillaries and they're taken away. In the nephron becomes more and more concentrated as it descends the loop of Henle. Now, this can never change. Once you are fully mature as an adult, you have particular lengths of loop of Henle. So this happens in a predictable way every single time that blood flows through your kidney. But different organisms have different lengths of loops of Henle. So for instance, organisms that need to retain more water will have longer loops of Henle. So if you were to look at, for instance, a camel and compare the loop of Henle of a camel to the loop of Henle of a beaver, something that lived in fresh water, don't know why that's the only animal I could just suddenly think of, then the camel would have a really long loop of Henle in comparison to the beaver because it would want to retain more water. This whole process is known as the counter current multiplier. This is a really important term. You've come across this term before. You learnt about it in year 12 when you learnt about exchange of gases in the lungs. Exchange of gases in fish gills. How the blood travels in opposite directions to the water, and so you've always got a higher concentration of oxygen in the water in comparison to what you do in the blood. The same principle applies here. This is a countercurrent multiplier. What it means is the solution in the descending limb is travelling in the opposite direction to the solution in the ascending limb. And what's happening in the ascending limb, i.e. the active transport of the sodium and chloride ions out, is causing or is increasing the osmosis that is occurring out of the descending limb. So what's happening in one side is affecting what's happening in the other. This process is called a countercurrent multiplier. And it's a funny thing because there are often just exam questions that expect you just to trot out that term for 1 mark. So it's worth remembering that term. I'm just going to show you this diagram because this diagram just shows you exactly the same stuff with just show you the whole process occurring at the same time. But that's basically everything that you need to know about the loop of Henle. So well done for listening, and I'll speak to you soon.